Hi, today we're going to do some pressure problems. I'm going to tell you how to set up the problems that I assigned since I think they're a little bit difficult. But first, I'd like to congratulate Anna Lieberman and Kirsten Strausser on their honors that were announced today. Okay, so we've got two different formulas for pressure. The first one is force over area. Force has to be in newtons. So if you get kilograms, you have to multiply that by 9.8. Make sure your area is in square meters. And when we do go through the problem setups, I'll show you exactly how to do that. This pressure formula is density, gravity, height. So the density, this is for things that are submerged in water, how much pressure is on them, or another liquid. You need the density of that liquid. And I did give you a density chart. So let's go through the example in the book, which is a density, gravity, height problem. Okay, the surface of the water in a storage tank is 30 meters above the faucet in the kitchen of a house. What is the water pressure at the faucet? So, density, gravity, height. The density of water is about 1013. Gravity is 9.8, and they told you that the storage tank is 30 meters above the faucet. So, we multiply those three numbers together, and you get... do that again. 1013 times 9.8 times 30. You get almost 300,000. About 297,822. This is in newtons per square meter, which is also a Pascal. That is one of the units we use for pressure. Here's the other ones: atmospheres and millimeters of mercury. Millimeters of mercury, that's when you measure something with a barometer, and the liquid in a barometer is usually mercury, and how much it rises, you measure that in millimeters. Okay, so that's the example. Let's go to number 8, which I believe is the first one I assigned in the back of the chapter. The pressure exerted on the floor by a model standing on a spike heel. Compare it to an elephant standing on 1 foot. So, let's get some space here. And this is going to be force over area. So we've got a model, pressure equals force over area. She has a mass of 50 kilograms. She's 50 kilograms. Now we've got to multiply that by 9.8 because we need force. Now, her spiked heel is 0.05 centimeters. Now, when you convert centimeters to meters, you move the decimal 2 places. But when it's square centimeters to square meters, it's 2 dimensions. So it's 4 places. So a 0.05 square centimeter heel, you got to move this 4 places this way, which is going to make this number huge. So we, instead of 0.5, you got 1, 2, 3, 4, 0.5. 1, 2, 3, 4. That's square meters. So when you work this out, the number's huge. It comes out to 98 million pascals. 98 million pascals. So this is why you're not allowed to wear spiked heels. Women can't wear spiked heels like when they go to a, on a wood floor or basketball court, because it really makes marks in the wood. Okay, so now let's look at the elephant. The elephant is a 1,500 kilogram elephant. Multiply that by 9.8. Now he's 1 foot. His 1 foot is 800 square centimeters. 800 square centimeters. We're going to move it 4 places. 1, 2, 3, 4. 0.08. So even though the numerator is very large here, it's going to give us 183,750 pascals. So, this is just one of those problems where they want you to see that the pressure of an average woman on a spiked heel is so much bigger than an elephant standing on 1 foot. And I'm going to stop the video there, and I'll come back and set up a few more problems.